Hey, come here. Yeah, just settle in. Get comfortable. Are you comfy? Good. Tonight, we are going to do something a little different. We are going to do some math together, but not the scary kind. Not the kind where someone is standing at a chalkboard yelling at you. No. This is the gentle kind. The kind where we just talk through things slowly, quietly. And if you fall asleep, that is honestly the best compliment you could give me. So just breathe, nice and slow, in and out. There is nowhere you need to be right now. Nothing you need to do. Just you and me and some very calm numbers. Okay, so let us start with something really simple. And I mean really simple. Like, what even is algebra? You have probably heard the word 1,000 times. Teachers love to throw it around like everyone is supposed to just know. But let us actually talk about what it means. Algebra is basically a way of finding things you do not know yet. That is it. That is really all it is. You have got some information, and there is a missing piece. And algebra is just the quiet, patient process of figuring out what that missing piece is. Think of it like this. Imagine you are baking cookies, and the recipe says you need a certain amount of sugar, but the label fell off the sugar bag. You know you added some already. You know how many cookies you ended up with. So you can kind of work backwards to figure out how much sugar was in that bag. That is algebra. You are just working backwards from what you know to find what you do not know. Now, the thing that scares people about algebra is the letters. The X and the Y, and I get it. When you are used to nice, friendly numbers, and then suddenly there is an X sitting there looking at you. It feels weird, but X is not scary. X is just a placeholder. It is like when someone says, "Hey, save my seat," and they put their jacket on the chair. The jacket is not the person. It is just holding the spot until they get back. That is X. It is holding the spot for a number that we have not found yet. So let us find a number, yeah. Let us start really, really gently. Here is our first little problem. Just a tiny one. Are you ready? X plus 3 equals 7. That is it. That is the whole thing. X plus 3 equals 7. Now, what is X? What number, when you add 3 to it, gives you 7? And you might already know the answer. You probably do. It is 4. Because 4 plus 3 is 7. Simple, right? Beautiful, even. There is something really satisfying about that. 4 plus 3, 7. Everything balances. But let us talk about how we got there. Not just by guessing, but by thinking about it in the algebra way. Because that is what is going to help us when things get a tiny bit more complicated later. So we have X plus 3 equals 7. And what we want to do is get X all by itself. We want X to be alone on one side of the equal sign, like giving X its own little room where it can relax. So we need to move that 3 away from X, and the way we do that is we subtract 3 from both sides. Both sides. That is the key. Whatever you do to one side, you do to the other. It is like a seesaw. If you take weight off one side, you have to take the same weight off the other side, or the whole thing tips over. Balance. Always balance. So x plus 3 minus 3. Well, the plus 3 and the minus 3 cancel each other out. They just dissolve like sugar in warm water. And we are left with just x. And on the other side, 7 minus 3, that is 4. So x equals 4. And there it is. Quiet, simple, peaceful. Let us do another one. Because that felt nice, right? There is something almost meditative about it. Finding the answer. Watching everything settle into place. Okay, how about this one? 2x equals 10. 2x, that means 2 times x. 2 multiplied by some mystery number gives us 10. So what is x? Well, if adding was undone by subtracting, then multiplying is undone by dividing. So we divide both sides by 2. 2x divided by 2 is just x. And 10 divided by 2 is 5. So x equals 5. Because 2 times 5 is 10. Perfect. You know what I love about this? Every problem is like a tiny little puzzle. And when the answer clicks, there is this moment of, oh, that is it. That is the one. It is like finding the right key for a lock. You hear that little click and everything opens up. Let us get just a tiny bit more interesting. Nothing scary, I promise. Just a little more to think about. How about 3x plus 5 equals 20? Okay, so now we have two things happening to x. First, it is being multiplied by 3. And then 5 is being added. So we need to undo both of those. And the trick is, we undo them in reverse order. We peel back the layers, one at a time, like unwrapping a gift very slowly. The last thing that happened to x was adding 5. So the first thing we undo is subtracting 5 from both sides, of course. Always from both sides. 3x plus 5 minus 5. The 5's cancel. And we get 3x on the other side. 20 minus 5 is 15. And now, we just divide both sides by 3. 3x divided by 3 is x. 15 divided by 3 is 5. So x equals 5. Beautiful. Let us just check that. 3 times 5 plus 5. 15 plus 5. 20. Yes, that is perfect. Everything checks out. Everything is in harmony. I want to take a little detour here, because I think this is important. A lot of people grew up being told they were bad at math. Teachers said it. Parents said it. Maybe they said it to themselves, and it stuck. It became this thing they carried around. I am bad at math. I am just not a math person. But here is the thing, and I really want you to hear this. There is no such thing as a math person. There are just people who had patient teachers, and people who did not. People who got the time they needed, and people who were rushed. Math is not about being smart or not smart. It is about going slowly enough to actually understand what is happening. And that is what we are doing right now. Going slowly. Letting things sink in. No rush. No pressure, just understanding. One step at a time. Okay, so I want to gently shift us into something a little different. Still math, still calm, but a different flavor. Let us talk about shapes, geometry, the study of shapes and spaces, and how things fit together. If algebra is about finding missing numbers, geometry is about understanding the world you can see and touch. The angles of a roof, the curve of a bridge, the way tiles fit together on a bathroom floor without any gaps, and the most basic shape, the one everything kind of starts with, is the triangle. 3 sides, 3 angles, simple and strong. Did you know that the triangle is the strongest shape in structural engineering? That is why you see them in bridges and roof trusses. Because a triangle does not collapse under pressure. It distributes force evenly across all 3 sides. There is a lesson in that, I think. So let us talk about triangles for a while. Just gently. The first thing to know about any triangle is that its 3 angles always add up to 180 degrees. Always. No matter what the triangle looks like. Fat, thin, tall, short. 180 degrees. Every time. So if someone tells you that a triangle has one angle of 90 degrees and another angle of 45 degrees, you can figure out the third angle, because 90 plus 45 is 135, and 180 minus 135 is 45. So the third angle is 45 degrees. And now you know something wonderful. You have a right triangle with 2 45-degree angles. That is a very special triangle. Mathematicians call it a 45-45-90 triangle. It is perfectly balanced, symmetrical, like a butterfly. Now, there is this one formula in geometry that I think is maybe the most famous formula in all of mathematics. You have heard of it. I know you have. The Pythagorean theorem. Let me say that again slowly. A squared plus b squared equals c squared. And what this means is, if you have a right triangle, the kind with a 90-degree angle in one corner, then the 2 shorter sides, A and B, their squares add up to the square of the longest side. The longest side is called the hypotenuse. Hypotenuse. It is a fun word, right? Just let it roll around in your mouth for a second. Hypotenuse. So let us say one side of a right triangle is 3, and the other side is 4. What is the hypotenuse? Well, 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. And the square root of 25 is 5. So the longest side is 5. 3, 4, 5. It is called a Pythagorean triple, a set of 3 whole numbers that perfectly satisfy the theorem. These are like little gems hidden in the number line, perfect combinations. You know, Pythagoras, the man this theorem is named after. He lived about 2,500 years ago in ancient Greece, and he believed that numbers were the fundamental building blocks of reality. Not atoms, not elements, numbers. He thought the entire universe could be understood through mathematical relationships. And in a lot of ways, he was right. The orbits of planets follow mathematical curves. Sound waves are described by frequencies and wavelengths. Even the spiral of a seashell follows a mathematical sequence. But Pythagoras also had a secret society, like an actual cult dedicated to mathematics. They had rules. One of the rules was that members were not allowed to eat beans. I am not making that up. No one is entirely sure why, but there it is. The father of one of the most important theorems in history was afraid of beans. Math people are weird, and that is okay. Let us talk about circles for a moment, because circles are, honestly, kind of magical. A circle is defined as the set of all points that are the same distance from a center point. That distance is called the radius, and the distance across the whole circle through the center is the diameter. The diameter is always twice the radius. Always. And then there is pi. 3.1415926535897932338. It goes on forever. Literally forever. Pi never ends, and it never repeats. It is what mathematicians call an irrational number, which does not mean it is crazy. It means it cannot be expressed as a simple fraction. It just goes on, infinitely. There is something almost spiritual about that, right? The circumference of a circle, the distance all the way around, is 2 times pi times the radius, and the area of a circle, the space inside, is pi times the radius squared. These formulas are elegant, compact, everything you need to know about a circle, wrapped up in 2 tiny equations. Let us calculate something together, nice and slow. Imagine a circle with a radius of 7, just 7, a small, friendly number. The circumference, the distance around, is 2 times pi times 7. 2 times 7 is 14. 14 times pi is approximately 43.98. So the distance around our circle is about 44. If you walked along the edge, you would walk about 44 steps, give or take, and the area inside is pi times 7 squared. 7 squared is 49. 49 times pi is approximately 153.94. So there are about 154 square units of space inside our little circle. I just love how everything flows from knowing just one thing, the radius. You know one number, and the entire circle reveals itself to you. Okay, now I am going to take us somewhere that sounds intimidating, but is actually really, really beautiful once you see it. Trigonometry. Trig. Even the word sounds serious, right? But stay with me. I promise this is going to be gentle. Trigonometry is really just the study of the relationships inside triangles, specifically right triangles. That is it. It is not some impossible abstract thing. It is about triangles, and you already know about triangles. You are already friends with triangles. So here is the setup. Imagine a right triangle. One angle is 90 degrees, and we are going to focus on one of the other angles. Let us call it theta. Theta is a Greek letter that mathematicians use for angles. Now, relative to that angle theta, the three sides of the triangle have names. The side opposite theta is called the opposite side. The side right next to theta, but not the hypotenuse, is called the adjacent side. And the longest side is still our old friend, the hypotenuse. And here is where the magic happens. Three ratios, three simple ratios, and they describe everything. Sine of theta equals opposite over hypotenuse. Let me say that slower. Sine of theta equals the opposite side divided by the hypotenuse. Cosine of theta equals adjacent over hypotenuse, the side next to the angle, divided by the longest side. And tangent of theta equals opposite over adjacent, the side across from the angle, divided by the side next to it. There is a mnemonic for this that you might remember. So, CAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So ka tower. Let us use this. Imagine a right triangle where the angle theta is 30 degrees and the hypotenuse is 10. What is the length of the side opposite the 30-degree angle? Well, sine of 30 degrees is 0.5. That is just a fact. Sine of 30 is 1/2. So, sine of theta equals opposite over hypotenuse. 0.5 equals opposite over 10. To find the opposite side, we multiply both sides by 10. The opposite side is 5, half the hypotenuse. Simple, clean, elegant. And the adjacent side, we can use cosine for that. Cosine of 30 degrees is approximately 0.866. And if you check with the Pythagorean theorem, 5 squared plus 8.66 squared, 25 plus 75, 100. The square root of 100 is 10, which is our hypotenuse. Everything checks out. Everything balances. You know what is amazing about trigonometry? It is everywhere. And I mean everywhere. When engineers build a bridge, they use trig to calculate the forces on each beam. When your phone uses GPS, it is using trig to triangulate signals from satellites when musicians tune their instruments. The sound waves are described by sine and cosine functions. Even the way light bends when it passes through water, that is described by Snell's law, which uses sine. The rainbow you see after a rainstorm, that is trigonometry. The way shadows change length throughout the day, trigonometry. It is this quiet, beautiful language that the universe speaks. Let us come back to algebra for a little while. I want to talk about something called linear equations and graphing, because there is something really soothing about drawing a straight line on a graph. A linear equation is any equation that, when you graph it, gives you a straight line. The most common form is y equals mx plus b, where m is the slope and b is the y-intercept. The slope tells you how steep the line is, how quickly it rises or falls as you move from left to right. A slope of 1 means for every 1 step you take to the right, the line goes up 1 step. A slope of 2 means it goes up 2 steps, steeper. And the y-intercept, that is where the line crosses the y-axis, the starting point, where the line begins its journey. So let us draw a line together in our minds. The slope is 2. The y-intercept is 1. So the line starts at the point 0, 1. Now, if x is 1, y is 2 times 1 plus 1, which is 3. If x is 2, y is 2 times 2 plus 1, which is 5. If x is 3, y is 2 times 3 plus 1, 7. And if you connect those points, you get a straight line climbing upward, steadily, predictably. Each step to the right, the line goes up by 2. Consistent, reliable, like a heartbeat on a monitor. Now, what about negative slopes? A negative slope means the line goes down as you move to the right. That line starts at 4 on the y-axis, and for every step to the right, it drops by 1. Down, 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 like a gentle hill leading to a valley. The line crosses the x-axis at 4, and then it keeps going into negative y values below the axis, into the quiet spaces underneath. There is something poetic about a graph, I think. A line is like a story. It has a beginning, a direction, a journey. Parallel lines have the same slope, but different y-intercepts. They are moving in the same direction, at the same angle, but they started in different places, and so they never meet. Perpendicular lines. Those are lines that meet at a right angle, 90 degrees, and their slopes are negative reciprocals of each other. If one line has a slope of 2, the perpendicular line has a slope of negative 1/2. I want to tell you about something called the unit circle, and I know that sounds technical, but it is actually one of the most elegant things in all of mathematics. So just stay with me. The unit circle is a circle with a radius of 1, just 1, centered at the origin of a graph, at 0, 0. and it connects algebra, geometry, and trigonometry all into one beautiful picture. Imagine you are standing at the point 1, 0 on the right side of the circle. Now imagine you start walking along the edge of the circle, counterclockwise, slowly. As you walk, your position changes. And here is the magical part. At any point along the circle, your x-coordinate is the cosine of the angle you have traveled, and your y-coordinate is the sine of the angle you have traveled. At 0 degrees, you are at 1, 0. Cosine of 0 is 1. Sine of 0 is 0. At 90 degrees, you have walked a quarter of the way around. You are at 0, 1. At 180 degrees, you are at negative 1, 0. At 270 degrees, you are at 0, negative 1. And at 360 degrees, you are back where you started, 1, 0. You have made one full trip around the circle, and you can keep going, around and around. The sine and cosine just keep cycling, up and down, back and forth, like breathing, like waves on a shore. Sine is a wave. If you plot sine against the angle, you get this smooth, rolling curve. It starts at 0, rises to 1 at 90 degrees, falls back to 0 at 180, drops to negative 1 at 270, and returns to 0 at 360. Then it repeats, forever. This endless, gentle wave, rising and falling. It is the shape of ocean waves. It is the shape of sound. It is the shape of alternating electrical current flowing through the wires in your wall right now. Sine is everywhere. It is the mathematical heartbeat of the universe. And cosine is the same wave, just shifted. Cosine starts at 1 instead of 0. It leads sine by 90 degrees. They dance together, always in sync, but never quite in the same place at the same time, like partners in a waltz. Before we drift too far, I want to come back to algebra one more time, because there is one more type of equation I want to whisper to you about. Quadratic equations. A quadratic equation has an x squared in it. That is the defining feature. Something squared. The general form is. And when you graph a quadratic equation, you get a parabola. A smooth, U-shaped curve, or an upside-down U, depending on the equation. Think about tossing a ball into the air. The path it follows, up, 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 slowing down, reaching the peak, then coming back down. That path is a parabola. Nature draws parabolas everywhere. Now, the famous formula for solving quadratic equations is the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. The square root part, b squared minus 4ac, that is called the discriminant. And it tells you something really important. If the discriminant is positive, you get two answers. If it is 0, you get exactly one answer. And if the discriminant is negative, there are no real answers. Let us try a gentle one. Here A is 1, B is -5, C is 6. The discriminant is B squared minus 4ac. The discriminant is 1. That is positive, so we will get two answers. X equals -5, which is +5, plus or minus the square root of 1, which is just 1, all over 2. So x equals 5 plus 1 over 2, which is 3, or x equals 5 minus 1 over 2, which is 2. And we can check. 3 squared minus 5 times 3 plus 6. 9 minus 15 plus 6. 0. Perfect. And 2 squared minus 5 times 2 plus 6. 4 minus 10 plus 6. 0. Both answers work. Everything balances. And you can also solve that one by factoring, because -2 plus -3 is -5, and -2 times -3 is +6. So either x minus 2 is 0, meaning x is 2, or x minus 3 is 0, meaning x is 3. Same answers. Different path to get there, like two different roads leading to the same quiet village. Let me whisper to you about exponents for a little while, because they are simpler than people think. An exponent just tells you how many times to multiply a number by itself. 2 to the power of 3 means 2 times 2 times 2, which is 8. That is it. 3 to the power of 4 means 3 times 3 times 3 times 3. 81. You are just repeating the multiplication, stacking it up. See how fast it grows. It doubles every time. That is the nature of exponential growth. Steady, relentless doubling. And this is why people talk about exponential growth being so powerful. If you fold a piece of paper in half, and then in half again, and you could somehow keep folding it 42 times, the thickness of that paper would reach the moon. 42 folds. That is the power of doubling. Square roots are the opposite of squaring. If 3 squared is 9, then the square root of 9 is 3. You are going backwards, undoing the exponent, like pressing rewind. These are the perfect squares, the numbers that have whole number square roots, and there is something deeply satisfying about them. They are like stepping stones across a river, solid, dependable. And then there are the numbers in between. The square root of 2 is about 1.414. It is irrational, like pi. It goes on forever. These numbers exist in the spaces between the stepping stones, in the flowing water, always moving, never quite captured. I want to take us somewhere that a lot of people find confusing at first. But once you see it, it makes perfect sense. Negative numbers, the numbers below 0, the numbers on the other side. Think about a thermometer. 0 is right there in the middle. Above 0, temperatures are positive, but below 0, things get cold. -1, -5, -20. Negative numbers are not imaginary or fake. They are real. And the rules for working with negative numbers are actually really intuitive once you think about them. Adding a negative number is the same as subtracting. 5 plus -3 is the same as 5 minus 3, which is 2. Subtracting a negative number is the same as adding. 5 minus -3 is the same as 5 plus 3, which is 8. It is like a double negative in English. And multiplying negatives has this beautiful symmetry to it. A positive times a positive is positive. A positive times a negative is negative. A negative times a positive is also negative. But a negative times a negative is positive. And this is the one that confuses people. Think of it this way. If losing money is negative, and reversing a loss is also negative, then reversing a loss is actually a gain. A positive. 2 negatives make a positive. It is like turning around twice. You end up facing the same direction you started. There is a beautiful pattern here. -1 times -1 is 1. It alternates, back and forth, like a pendulum swinging. Let me tell you about ratios. Because ratios are one of those things that people use every single day without even realizing it. A ratio is just a comparison. That is all. If there are 2 cats and 3 dogs in a room, the ratio of cats to dogs is 2 to 3. And proportions. Proportions are when 2 ratios are equal. You doubled both numbers, but the relationship stayed the same. The comparison did not change. This is how recipes work. If a recipe for 4 people needs 2 cups of flour, then a recipe for 8 people needs 4 cups. The ratio stays the same. Let us solve a little proportion together. If 3 notebooks cost $6, how much do 7 notebooks cost? We cross multiply. 3 times x equals 6 times 7. Divide both sides by 3. 7 notebooks cost $14 because each notebook is $2. The ratio holds. Before we start to wind down, I want to paint a picture for you. The number line. Just close your eyes and imagine it. A line stretching infinitely in both directions. To the left, negative numbers extending forever. And to the right, positive numbers going on forever, never ending. And right in the middle, 0. The point of perfect balance. Neither positive nor negative. The calm center of an infinite line. Between every 2 whole numbers, there are fractions. Between 0 and 1, there is 1/2, 1/3, 1/4. And between any 2 fractions, there are more fractions. An infinite number of fractions between any 2 points. And scattered among the fractions, like stars hidden in a dark sky, are the irrational numbers. Pi, the square root of 2. Euler's number E, the golden ratio phi. Numbers that cannot be written as fractions. They live on the number line 2, in the spaces between the fractions, hiding, infinite, mysterious. The number line contains everything. Every number that ever was or ever will be. It is all there, stretched out in both directions, infinite and complete. Okay, one more topic before we really start to wind down. Sequences. And I promise this one is perfect for falling asleep too. A sequence is just a list of numbers that follow a pattern. That is it. A list with a rule. The simplest kind is an arithmetic sequence. That is where you add the same number each time. Each time we add 3. The common difference is 3, and you can keep going forever. To find any term in an arithmetic sequence, you use the formula, where a sub 1 is the first term, n is which term you want, and d is the common difference. So if the first term is 2 and the common difference is 3, the 10th term is 29. You can jump to any term you want. And then there are geometric sequences. Those are where you multiply by the same number each time. Each time we multiply by 3. These grow much faster than arithmetic sequences. An arithmetic sequence walks. A geometric sequence runs, then sprints, then flies. And if the common ratio is less than 1, the sequence shrinks, getting smaller and smaller and smaller, approaching 0, but never quite reaching it. Like a whisper getting softer and softer until you can barely hear it. But it never quite disappears. There is something deeply calming about sequences. They are predictable, ordered. You always know what comes next. Even numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Steady, reliable. Perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Getting further apart each time, the gaps between them growing. 1 to 4 is 3, 4 to 9 is 5, 9 to 16 is 7. The gaps are always odd numbers. Always. That is a beautiful little secret hidden in the perfect squares. Now I want to take us somewhere new. We have been living in the world of pure math, numbers and shapes and equations. But math does not live alone. It has a best friend. And that best friend is physics. Physics is just math in motion. Math wearing a lab coat and asking, why does the world work the way it does? And the answers are surprisingly gentle. Let us start with something you feel every single day. Gravity. You are lying there right now, and gravity is pulling you softly into your bed, into your pillow. It is the reason you feel grounded, safe, held. And Newton described it with one beautiful equation. Force equals mass times acceleration. That is it. That tiny equation describes everything from a feather falling to a planet orbiting the sun. The same law, the same quiet truth, everywhere, always. Think about a pendulum, just a weight hanging from a string, swinging back and forth, back and forth. The period of a pendulum depends on its length, not the weight, not how hard you push it, just the length. There is something deeply soothing about that. The universe keeps things simple when it can. Now imagine you are at a playground. There is a lever, a seesaw. A child sits on one side, an adult on the other. But if the adult sits closer to the center, to the fulcrum, it balances. Because torque is force times distance. The physics of balance, of equilibrium, and simple machines are everywhere. A pulley lets you lift heavy things with less effort. An inclined plane, a ramp, lets you climb to great heights gradually instead of all at once. Humans have been using these for thousands of years. The pyramids were built with ramps and levers. Physics in the ancient world. Let us talk about waves for a moment, because waves are hypnotic. Sound is a wave. Light is a wave. The ocean moves in waves, and they all follow the same mathematics. A sine curve stretching out, rising and falling, rising and falling. When you hear a note on a piano, that is a standing wave vibrating inside the instrument. The string vibrates at specific frequencies, specific harmonics, and each harmonic is a whole number multiple of the fundamental frequency. Music is math. The first harmonic, the second harmonic, the third, each one an integer, each one perfectly ordered. The physics of music is the math of beauty. And light. Light does something wonderful when it passes from one material to another. It bends. This is called refraction. When you put a straw in a glass of water and it looks broken, that is refraction. Light slowing down and changing direction. And when light passes through a prism, it spreads into a rainbow. Red, orange, yellow, green, blue, violet, each color bending at a slightly different angle, each wavelength finding its own path, diffraction and refraction, turning white light into a symphony of color. Here is one more physics idea for tonight: the Doppler effect. You know how an ambulance siren sounds higher pitched as it approaches, and then lower as it drives away? That is because the sound waves are being compressed in front and stretched behind. The frequency changes, but the ambulance siren itself never changes. It is your perspective that changes, and there is something philosophical in that. Okay, let us go even smaller now. Smaller than anything you can see. Smaller than a grain of sand. Smaller than a cell. We are going into the world of atoms. Welcome to chemistry. Every single thing you can touch, see, smell, taste is made of atoms. Your pillow, the air you are breathing, the phone or screen near you. All atoms. incredibly tiny building blocks making up everything in the universe. And an atom has a beautiful structure. At the center is the nucleus, protons and neutrons packed tightly together. And around the nucleus, electrons orbit in shells, like tiny planets around a tiny sun. The first shell holds 2 electrons. The second holds 8. The third holds 8 more. And the way those shells fill up, that is what determines everything about an element, how it behaves, what it bonds with, its personality. The periodic table is like a map of every element that exists. Hydrogen is number 1, just 1 proton, 1 electron, the simplest atom in the universe. And helium is number 2, 2 protons, 2 electrons, a full first shell. Content, stable, noble. And this is why helium does not react with anything. Its electron shell is full. It has no reason to bond. It is complete on its own. The noble gases, helium, neon, argon, they are the introverts of chemistry, perfectly happy alone. But most elements are not like that. Most elements want to bond. They want to share electrons, or give them away, or take them from others. And that desire to bond, that is what creates molecules. Water, H2O, is 2 hydrogen atoms bonded to 1 oxygen atom. The oxygen shares electrons with each hydrogen, a covalent bond, a partnership. And the angle between those 2 bonds is 104.5 degrees. Not straight, bent. That bend is what gives water its remarkable properties. And then there is benzene, a ring of 6 carbon atoms, each bonded to a hydrogen, with electrons flowing around the ring like a tiny highway. It is one of the most important molecules in organic chemistry, and its shape, a perfect hexagon, is quietly beautiful. In the lab, chemists use tools that have barely changed in centuries. Test tubes, beakers, the Erlenmeyer flask with its triangular body and narrow neck, a Bunsen burner with its steady blue flame. There is something timeless about it. Scientists standing over a beaker, watching a reaction happen, just like they did 200 years ago. And reactions, chemical reactions, follow rules. Every reaction has an energy diagram. Reactants start at one energy level. Products end at another. And in between, there is a hill, the activation energy, the push you need to get the reaction started, like pushing a boulder to the top of a hill, and then watching it roll down the other side. Some reactions release energy. Exothermic. Combustion is exothermic. A match burning. A candle flickering. Energy flowing outward as heat and light. Some reactions absorb energy. Endothermic. An ice pack getting cold when you crack it. Energy flowing inward. And the pH scale. It measures how acidic or basic something is. 0 to 14. 7 is neutral, pure water. Below 7 is acidic, lemon juice. vinegar. Above 7 is basic. Soap, baking soda. Each step on the pH scale is a factor of 10. So something with a pH of 3 is 10 times more acidic than something with a pH of 4, and 100 times more acidic than pH 5. Logarithmic, like the Richter scale for earthquakes. Math hiding inside chemistry. Let us zoom out now, way out, past the atoms, past the molecules, past the earth itself. Let us look up at the sky. The universe is impossibly large, and yet math can describe it. That is the miracle. That equations written on a chalkboard can predict the motion of galaxies billions of light years away. Our solar system is a beautiful piece of orbital mechanics. Each planet follows an elliptical orbit around the sun, and Johannes Kepler figured this out 400 years ago. Without a computer, without a telescope, just math, patient, careful math. The distances are staggering. Light travels at 300 million meters per second, and it still takes over 8 minutes for sunlight to reach Earth. 4 years to reach the nearest star. 100,000 years to cross our galaxy. The numbers are so large they become poetic. And then there is gravity again. Einstein showed us that gravity is not a force pulling you down. It is the curvature of space-time itself. Mass bends the fabric of space and time. The sun creates a dip, a well, and the earth rolls around that curve, like a marble rolling around the inside of a bowl. A black hole is where that curvature becomes infinite, where space bends so much that nothing, not even light, can escape. The math still works, the equations still hold, but the numbers become infinite. A singularity, mathematics at its most extreme. And on the smallest scale, quantum physics tells us that particles do not behave like tiny billiard balls. They behave like waves. A wave function describes the probability of finding a particle in a certain place. Not certainty, probability. The universe at its core is not deterministic. It is probabilistic. Even math has to get comfortable with uncertainty down there. The wave function, written with the Greek letter psi, it contains everything we can know about a particle. Its position, its momentum, its energy, all encoded in one beautiful function. And here is something that connects the very large to the very small. The same math that describes electron shells in an atom also describes the orbits of planets. The same differential equations, the same patterns. As above, so below. The universe rhymes with itself. There is a number called Euler's number, E approximately 2.718. It appears everywhere, in compound interest, in population growth, in radioactive decay, in the shape of a hanging chain, in the normal distribution, the bell curve that describes how test scores and heights and so many natural things are distributed. Euler's identity combines 5 of the most important numbers in mathematics into one equation, EI pi 10. The 5 pillars of mathematics, all connected, all intertwined. Many mathematicians call this the most beautiful equation ever written, and I think they might be right. We have covered a lot of ground tonight, you and I: algebra, geometry, trigonometry, exponents, physics, chemistry, the universe itself. And I really hope, that none of it felt scary, because it is not scary. It is beautiful. And you know what the most wonderful thing about math is? It is always true. In a world where so many things are uncertain, math is constant. 2 plus 2 will always be 4. The angles of a triangle will always add up to 180 degrees. Pi will always be pi. I want to leave you with one more thought before you drift off. There is a sequence in math called the Fibonacci sequence. Each number is the sum of the 2 numbers before it. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. Simple rule, infinite complexity. And this sequence shows up everywhere in nature. The number of petals on a flower is almost always a Fibonacci number. Lilies have 3. Buttercups have 5. Daisies have 21 or 34 or 55. The spiral of a pinecone follows the Fibonacci sequence. The arrangement of seeds in a sunflower. The curl of a nautilus shell. Nature speaks mathematics, and the Fibonacci sequence is one of its favorite words. So that is it for tonight. That is our time together. You did so well. I am proud of you for being here, for listening, for being curious about numbers and shapes and patterns. If you are still awake, that is okay. Just keep breathing, slow and steady, in and out, and let the numbers float around in your mind like leaves on a pond. And if you have already fallen asleep, then good night. Sweet dreams. I hope they are full of gentle equations and quiet parabolas, and the soft rolling waves of sine curves stretching out toward infinity. Good night.